Okay, we have the system with a magnet and the cart. The cart has a magnet on it. We got a magnet here. We bring it so close, we release it. It goes so far across a level tabletop. Okay? And in that context, at proximity 3 centimeters, thing coasts this far. At proximity 2.7 centimeters, coasts a little further, right? So if the car has a mass of 50 grams, the coefficient of friction is 0.04, and that's implicitly the coefficient of kinetic friction because the thing is moving, so I don't really have to be specific about that, okay? Wouldn't hurt, but I didn't. We want to find the change of potential energy system from 2.7 centimeter proximity to the 3 centimeter proximity. So we ask for the relevant principles because naturally with a room full of engineers, people just want to start pulling out equations and putting stuff in them, okay? And that's an important skill, but this is physics. We come in and we think in terms of principles, which makes a better engineer out of you, also just a better problem solver in general. Identifying numbers that go into formulas and hopefully getting the right formula is a certain level of problem solving, but a deeper level is understanding the principles and then being able to move from principle to solution. Okay, so what relevant principles do we have? Well, the first comment I got was, do we have the time? Well, immediately that tells me that somebody's thinking in terms of the equations of uniformly accelerated motion. Natural enough, because many people in here are taking dynamics right now where you plug things into equations to get the right answers, right? There's more than that. I'm not knocking dynamics, it's great. And you got a lot of really subtle equations that are hard to connect with principles, so you got to be able to do that. But one thing that I've been trying to get across is that there are situations in which equations of uniformly accelerated motion don't work because the motion isn't uniformly accelerated. Okay? Now this motion, it turns out, does involve a constant net force on a constant mass, so it is uniformly accelerated. Okay? But we don't need to use acceleration. Anyhow, that comment led us to, well, what forces and so forth, and it led to the fact, well, we got the coefficient of friction, so we could hopefully find the frictional force. So the principle is, what's frictional force? Okay? We haven't talked all that much about it, but we've talked enough about it that you ought to have the idea that it's a product of the normal force and the coefficient of friction. Okay? At least kinetic friction for an object in motion. For static friction, the frictional force might be less than what you get when you multiply these because you might only have a little bit of force acting against the friction, and friction can't exert more force than what acts against it. Well, that's a little digression, but that's another kind of a principle, okay? Okay, well, then I think somebody mentioned the W thing, work, okay? And then we want to write down what work is. It's defined to be essentially the product of force and displacement, right? But you got to be careful because the force might not be along the same line as the displacement. So we say the perpendicular component of the force times your displacement, or F dot delta S, right? And these both apply if your force is constant. This applies if your force isn't constant, okay? And it actually leads to line integrals, but we're not doing line integrals in this course. Okay, but it does lead to an integral along a single axis. So we have this, and we have to understand, of course, why it's the dot product, because we have to know what the dot product is. Okay? So, when we get to problems that involve the dot product, hopefully understand what that is. Okay. Well, the one thing that I had to bring people's attention to was we have change in potential energy. Okay? How do you get the change in potential energy? Well, we already see, well, we got something about forces, we know what work is. And I say, okay, what's the definition of potential energy? Nobody could tell me much, even though this is something I told you to memorize verbatim a month ago and never forget. Clear? After we dragged this out of people word by word over a period of about 10 minutes, that nobody had bothered to memorize this definition. And now you have a problem that you're not going to solve unless you know this definition, okay? Because this definition is fundamental to the whole work energy theorem in terms of kinetic and potential energies, okay? So there's a principle here that you're not grasping. And since there's a test coming up in a couple of days, you want to grasp it quick, right? Okay? So, one thing. When I tell you something's really important, you got to know it verbatim. There are only less than this many things that I'm going to, statements that I want you to know verbatim in this course. Okay? This is one of them. Another is definition of an average rate of change, which I'm sure, because somebody mentioned the words equal, I'm not equal and opposite. With respect to, somebody thought about that one, okay? Well, you want to not just think about them, you got to know them, because you can't apply them if you don't know them, right? Otherwise, all you're doing is plugging numbers into formulas without understanding completely what you're doing. You're understanding at a profound level, but not completely. And we want complete understanding of everything we can get, okay? So these are a few of the principles. Now, where do we go from here?